So we're entering into section 1.8 where we're building on what we've learned in previous sections and starting to use it in interesting ways. Um, in this particular section, we're going to talk about linear transformations, sort of get an idea what they are, and then in the culminating section 1.9 of chapter 1, we'll look at linear transformations in more detail. Um, and we're kind of just thinking about things we've already done in that matrix multiplication, right? We've been looking at this equation, ax equals b. We're thinking about this in just a slightly different light. And so previously, in previous sections, we thought about this matrix equation as doing linear combinations of columns of A using the entries of x as the weights. Right, so this equation, ax equals b, translates into this vector equation from section 1.4. Actually, I was just looking at section 1.4 homework, where you talk about translating between these two things, right? We start with some linear system, and they can be written in both of these ways. And when we were doing it, when we were thinking about this, we were doing linear combinations of the vectors, but now we're thinking about shifting our approach to thinking about ax equals b as matrix A acting on vector x and transforming it into vector b. And so in this light, we're kind of thinking about it as an action. Right? And when you think about equations in this light, there's lots of applications in computer graphics, signal processing, data storage, lots and lots and lots of things. And in the next section, we'll kind of look at, just as I preview ahead to these future sections, we're looking at linear transformations of objects, and we'll actually see when that looks like this at the end of this section. And so I'd kind of like to think about linear transformations in something we're all familiar with, something like maybe Snapchat. All right, so we're going to think about matrices in some sense, the Snapchat filter acting on some vector, maybe in some sense a picture, and transforming it into something else. Right? It transforms your face or something into something that looks different. And so we're going to start thinking about this very simply just as reimagining matrix multiplication. Okay, so let's have this matrix A right here. Right, it's a 4 by 2 matrix. We've got vector x right here. And so if we multiply A times x, as we've seen previously, we're allowed to do this because this is a 4 by 2, as we just said. A is. X is a 2 by 1. And so these inner dimensions match up, and so we're allowed to multiply these two, this matrix and this vector. So let's go ahead and do it. Let's act, but in this sense, we're not going to multiply. We're going to think about A acting on x to produce this. Okay, so here we are multiplying A and x, A times x. And as we learned in the previous section, you kind of think about the vector x, at least I like to think about it, these entries stacking on top of the matrix, and the 3 is going to multiply down through the first column, the 2 multiplies down through the second column, and we do the linear combination of those two. All right, so we multiply the 3 times these to get these values, the 2 multiplies the other column to get these values, we add them together, and we obtain this new matrix. And again, thinking about this as a 4 by 2 and a 2 by 1, these dimensions match up, and then the outer dimensions we know creates the dimension of our final vector. But notice what happened here. X was a two-dimensional object, right? It was a 2 by 1, and this matrix A acted on it, and it was allowed to act on it because it had the inner dimension, correct? But it acted on it to produce a 4 by 1. And so in this sense, we actually change dimensions here, and we're going to think about this matrix as sending something from 2 dimensions to 4 dimensions. That's how we could characterize this particular matrix multiplication. So I just want to write that down. So in this light, we can think about A being a function that was applied to vector x, and that particular vector was two-dimensional, right? And so we say x is in R2. And what happened, it created a vector in R4. So we're thinking about this matrix transforming this vector. just kind of thinking back to Snapchat example. This isn't exactly how Snapchat works, but we can kind of think about it in a similar way. We can think about this as being our original picture, and somehow we have a different picture now that A has acted on it. And so the notation we would use in this sense is we would say that A is a linear transformation that sends vectors from R2, which would be X, into R4. So this arrow we kind of read as it gets sent to. It sends vectors from R2 into R4. Just kind of thinking about the lingo. So here's what's sort of going on visually. Just got some shadows here. Got some late afternoon light. Okay. Try to block that out. We like to look at these pictures visually a little bit in math. And so let's look at a similar situation that we just looked at, but one that more matches this picture. So in this picture right here, we're sending a vector from R4 and it's being sent to R2, right? And so let's create a situation that will do that right here. So for example, something that would do that, we would need something to be 2 by 4 to match up with those two. And so if we let our vector A be this, for example, right, we've got a 2 by 4, and see these are the dimensions that match up with these. If we multiply that by this X, which is now a 4 by 1. We're allowed to do it because the inner dimensions match. The result is going to be the opposite what we had up here, a 2 by 1. So, linear combinations, we use these as weights for linear combinations of the columns, and it becomes this. Let me know if you want to look at those details carefully. Hopefully by now we're able to kind of multiply those things together. And those add together, and just in this case happen to send to 0, 0, which we'll later learn is called the null space. But what I'd like to focus on right now is we just had the opposite situation that we had before, right? Before we took a 4 by 2 times a 2 by 1, and it became a 4 by 1. And so in this sense, we sent vectors in R2 to R4. And in this particular example, we've got a 2 by 4 times a 4 by 1, which is going to send something to 2 by 1. And so this is sort of visually this example right here, where here are vectors that live in R4. We can't really visualize it, but we're kind of thinking about them as living in that box. And multiplication by A is sending them to vectors in R2. Right? And so in this case, we're thinking A sends vectors that are in this case, R4 to R2. And so given these examples, seeing how this 4 by 2 sends things in 2 by 1 to 4 by 1, and things here, right, a 2 by 4 sends vectors in R4 to R2, we could make a general statement about matrices that are size m by n. We always want to kind of generalize these things. So maybe think about that for a second. How can we generalize this? Let me start this sentence. So matrix A, let's say, is an m by n. Some kind of butchered the script notation. There we go. It's okay. Sort of a script m. This is how we read matrices that are size m by n. Cool. So we've got this matrix. It's an m by n matrix. So we're thinking generally now. What is that going to do to vectors? That's going to send vectors, right? If it's m by n, they need to be n by 1. And then the result is going to be this dimension, right? The m. That's what we saw up here. And so we could say that this sends vectors in Rn, right? They're going to be n dimensional. vectors in our this dimension. And so anytime we do matrix multiplication, yes, we can, one, think about doing linear combinations of the columns like we did previously in 1.4, but we're just trying to move into this sort of different application of, again, graphics, signal processing, etc., where we're transforming something, and we're transforming dimensions in this sense. Let's just get a few vocab words out of the way. There's often different words actually for transformation itself. Sometimes people call it a transformation. That's what we'll mostly stick to in this book. You'll also see the word function or mapping in other courses, and generally these things are the same. So each of these three things have the same meaning. We often represent it generally with the script T, or capital T, for transformation in this case. And we say it's from Rn to Rm, right? So those are the dimensions of the matrix. And we're thinking about it as a rule that sends every vector in the first dimension to other vectors in the second dimension. Now note that n and m could be equal, right? It could be a square matrix in that case, in which case you'd be sending vectors, say, in R2 to other vectors in R2. That's certainly a possibility. And we'll see that actually on the next page. An example of it, excuse me. Okay. So here's another picture similar to the one on the last page. Now we're starting to name things, right? So remember, these are the dimensions we're dealing with. And it's also going to be the size of the matrix. And as we saw on the last page, the m is going to be the number of rows, and the n is going to be the number of columns. And so the number of columns, which is n, we call the domain. Right? It's the size of the things you're multiplying a by. In other words, it's the size of x. And we can think about it as a number of columns in A. And we see that it takes vectors that are size x, T does, and sends it to what we call the range. Now the range might be inside something else called the codomain. All right, let's dissect this and write a few of these things down. So the second dimension, Rm, we call the codomain, and it contains the range, excuse me. Right, so the range, it's possible that the range is the same size as the codomain, but it might not be. Now it does have to be a subset of the codomain. And this is the notation we often use. We say, and we'll write this down. We're going to write this down. It's very important that we understand what this means. You'll see this all the time in homework and things. And you don't want to be confused by simple notation that just means something very, very simple. And so we'll write it down in words so you can have it for later. This means the linear transformation T acts on vectors that are in Rn and sends them to vectors that are in Rm. Okay? So the linear transformation T acts on vectors in Rn and sends them to vectors in Rm. And again, it's possible that n and m are the same size, in which case the range and the codomain would be filled. If you have the same dimensions of the two things, then you're going to have the same. But if you don't, like we saw on the last page, in the last stage we saw something being sent from a larger dimension to a smaller dimension. right? And something like this, and in this one we saw something being sent from a smaller dimension to a larger dimension. Right? So if you have this case, what we'll end up seeing is you can't have a one-to-one function, right? Or excuse me, you can't have an onto function. You can't actually fill the space in a case like this, but you can fill the space in a case like this. I don't want to get too far ahead of ourselves, but we're starting to think about dimensions here, which is a very cool and interesting part of linear algebra. And so let's actually write down this second one right here, right? So in this second one, we were sending things from R4 to R2. And so R4 would have been the domain, right? That's where things were coming from, and they were getting sent to the range, would have been the inside part, would have been R2. So the last example on the last page, that transformation that we just looked at, sent vectors from R4 into R2. And so in this case, this was the domain. This is where things were coming from. And this was the codomain. Just as a couple of follow-up definitions. The vector that we say t of x, so this is the vector that's already acted on x, so it's like an output. That's in the Rm dimension. We call it, another word for that is the image. And the set of all images, we would say, is the range. So when we collect all the images, that's what actually creates this blue plane. One of them, so a single vector in the range, or in the domain, gets sent to a single vector in the range, right? You can see that right here. And then when we collect all of them, that's the actual range. And so another way to sort of think about the range, it's all the vectors of the form t of x. It's everything of vector we can collect up that's been acted on by the transformation. Let's start by looking at a very simple transformation, and then we'll look at a couple interesting ones, at least more interesting ones using pictures. So we do have some pictures here, but they're just lines and they're just vectors in this case. So what we're going to do with these vectors is we are going to create this very simple transformation. So this is saying when the transformation acts on vector x, it just equals rx, where r is a scalar. So if you want to act on a vector, you just multiply it by a scalar. Now there are two types of this particular simple transformation. There's the one that's where r is bigger than 1, and there's one where r is between 0 and 1. Right, if r is bigger than 1, we know that when we multiply a vector by a number bigger than 1, it just stretches it out. We've seen that visually. And so that's called a dilation. And so that's what's going on in this first situation. Let's make up a hypothetical transformation. Let's say when you apply this dilation to x, you just multiply the vector by 3. In other words, t, the transformation t, takes a vector and makes it 3 times bigger. And so this is exactly what's going on. Right here, there in R2, if we had a bunch of vectors in R2, and you applied t to these vectors, they'd stay in R2 because we're just multiplying it by 3, and it gets 3 times larger. Right, so we saw this sort of action when we were looking at scalar multiples of vectors, and now we're just thinking about it as a linear transformation. Now it's actually this linear transformation scaling things, right? Maybe this is the Snapchat that makes your face look bigger. Maybe if you hone in on this Snapchat around your nose pops out on the Snapchat or something like that. A contraction would be the opposite, where something shrinks. And so we could do the exact same thing, just make the thing we're multiplying by less than 1, or a fraction, and that would be a contraction. And in this case, it just makes everything smaller. So just sort of rethinking now simple vector scalar multiplication. Now thinking about it as a dilation or contraction, where we're just shrinking or expanding vectors. All right, let's apply that same sort of idea to a picture. Okay, so we've got this matrix A. This is going to be our linear transformation matrix. And this matrix is doing this. This is a visual of our transformation, right? It takes things that are in R2, we transform them using this matrix, and it makes it look like this. And so this is how we define this transformation. It takes vectors that are in R2, and it keeps them in R2. So it's a square matrix. Oh, wait, that's why A is 2 by 2, right? So A is a 2 by 2, and since it's 2 by 2, we know that it's taking things in R2 and keeping them in R2. Now, we're defining this transformation by matrix multiplication. So this is saying we take a vector in R2, and all we do is we multiply it by matrix A. Well, let's see what happens when we do that. This is called the shear transformation. And this is visually what it does. So how is it that just multiplying vectors by this matrix does this to a picture? Let's hone in on pieces of that picture and find out. So let's hone in on this point with blue. That's the point 2, 0, or excuse me, 0, 2. Let's hone in on this point right here. That's the corner of the box at the point 2, 2. Let's hone in on the point right here. This one is 2, 0. And I need to grab another color pen. It might. Let's hone in on this point right here. That's the origin. It's 0, 0. And what we're going to do is we're going to see how each one of these points gets transformed into this new picture just simply by matrix multiplication, right? So we're honing in on this definition right here using this matrix A. Okay, and our vectors x are these individual vectors. Each one of these is going to be a vector x. And so what we're going to see, kind of the punchline here, is T is going to act on all the vectors in this box, that box, and transforms them into the following. All right, so we're going to look at the corners and see what happens to the corners, and then what happens between the corners will be obvious as well. And so let's act on the origin first. So I'm going to do that in green. All right, so let's act on this linear transformation on 0, 0, that point. Well, this definition just says, okay, when you act on a vector, just multiply by matrix A. So we take matrix A and multiply by 0, 0. Well, we've already seen that when you multiply something by 0, 0, it just stays 0, 0. But just to be clear, it's because you're doing linear combinations of these with the columns, and since you're just multiplying by 0, you just end up adding a bunch of zeros together. And so this one actually doesn't move, right? When this matrix acts on 0, 0, it stays at 0, 0. And notice in the picture, that's what happened. This point, after it got acted on, stayed right there. It's still at the same spot. All right, let's act on this corner right here, 0, 2. So we multiply by matrix A. Right, we're just doing A times X again, where we have a new X. And we do linear combinations of the columns. Whoa, okay, so this one changed. Right, we acted on this vector, and now it's at 6, 2. So that's what's going on right here, right? This is the point 6. And so we see that this one, when it got acted on, went over to here. So t acted on that corner and shifted it over there. And so that's what's giving it this, the way that this thing's you kind of think about it. It's like you put something down and you grab it at the bottom, you grab it at the top. You keep the bottom one still, but you move the top over. Right, that's what would happen if you did something with this, right? So it's kind of shifting it over, it's shearing it, it's what it's called. All right, let's act on the next corner. Let's act on 2, 2. And so this one should also shift, just looking at the picture, and let's see that happen. So we do a times x times 2, 2. This is going to be 2 plus 6, so 8. 0 plus 2. So it becomes 8, 2. Right, and we see that here. Same kind of thing. This corner got acted on, went right over here. Notice how the second dimension on these ones aren't changing, right? So the height's not changing on here. It's just that the x value gets shifted over. Again, if you grab this, you grab the top and you shifted it over, you're not making it taller, you're just shifting the x value, which is exactly what's going on these things. And we'll just finish off and see the last one. So let's act on 2, 0. Do the matrix multiplication. It's going to be 2 plus 0, 0 plus 0, 2, 0. So that one doesn't move either, actually, right? Oh, yeah, we see that here. This one, acted on, doesn't move. Right, so we're not actually shifting the bottom at all, we're shifting the top over. And if we acted on all the points in between, we'd also see them fall right in this shifted box. Right, so this is called the shear transformation. And we're starting to see how when we think about it's just matrix multiplication, right? We're just multiplying a times x, but when we apply it to a picture, it might actually change the picture. And so again, kind of thinking to our Snapchat example, we're thinking how this might be applied. This is the joke in the book. I did not come up with this, but it's kind of funny, right? It's kind of like if we had a picture of something, like let's say we had a sheep. Whoops, this should be x1, x2. And then we apply the transformation to that picture, right? So apply it to all the points in the image. It becomes a sheared sheep, ha ha ha. Right, so it's kind of like we grab the sheep, apply the transformation, so multiply all the vectors by a, keep the bottom still, move the top one, shift it over, and it would look like this, a little distorted. Right, just so if anyone's just reading this, I just want to write that down. If we actually applied t to a picture, so that image right above, or that matrix right above, right? And we'll talk about how it has the identity matrix in there, but it's actually multiplying by 3, the second dimension. That's what calls the shift. We just literally applied that matrix multiplication to a picture like this. It would shear the image. Right, it would slide it over. We're going to look at that in a little more detail actually in the next section, and we'll look at some more box examples and see how different types of transformations do different things to boxes. All right, this chapter just finishes off with a couple quick properties. So here's a definition of a linear transformation. We've kind of dove right in to look at some examples of them, but here's what an actual definition of a linear transformation is. And the linear part is important, right? So a transformation or mapping is linear, right? So there's non-linear transformations, in other words. But we're talking about a linear transformation has these two properties. If you apply a transformation to the sum of two vectors, it's the same thing as just applying the transformation to the vectors separately. Right? So in other words, that's what it means practically. Mathematically, it means you can just do the transformation separately and then add together the result. Excuse me. The second one talks about if you've got a scalar multiple of a vector, so c is a scalar in this case, you can just pull the scalar right out front. In other words, when you apply the transformation to a scaled version of the vector, it's the same thing as just scaling the output of the transformation. And the idea is that this definition leads to these properties. So these right here lead directly to these properties. All right, so for example, if we plug a 0 in here, I'm sorry, if C was 0, then this would say C of 0, T of 0, excuse me, equals 0. Right, so that's where that property comes from. And then we could also sort of combine the two together to get this. Right, so you could break it up if there was a constant in there and then pull the constants out. And so these are two very typical properties of linear transformations. We're going to sort of do a quote-unquote proof in a second, although I've already sort of talked about how it works. But let's just explain this again. So this one's talking about how linear transformations send the 0 vector to the 0 vector. Right, so any kind of linear map is always going to send the 0 vector to the 0 vector. The second one, again, I sort of talked about it in words, but this is also kind of looked at as a sort of like a distributive or multiplicative property, right? You can kind of think about it distributing through there and then pulling out constants, right? And so this is kind of like, it's not really, but I'm going to put it in quotes. It's kind of like a distributive and multiplicative properties. And so let's use these properties to show that we've got a linear transformation. So let me bring that last page back. All right, we've got our linear transformation from the last page, going from R2 into R2. I just realized this is missing a t for some reason. This should be t of x. And so here's our linear map from the last page, right? T of x equals rx. Oops, 2 pages ago. So we're looking at this same contraction or dilation mapping. And since we've got it between 0 and 1, it's actually a contraction. Let's show that this is actually a linear transformation by showing it satisfies these two properties. So number 1, let's apply it to the 0 vector. This says if we've got a linear map, it just stays 0, right? Well, this linear map, when you apply it, you just multiply r times the 0 vector. And when you multiply anything times the 0 vector, it stays the same. And so property 1 above here is satisfied. The second property is the distributive one, right? And so let's show that when you apply this transformation to a scalar, a linear combination of u and v, it actually satisfies this property. And so this mapping tells us when you want to apply the matrix, excuse me, the transformation to a vector, just multiply by r. And so this becomes this. Right, we're just following this instruction here and multiplying by r. Well, now that we've got a scalar here, we can distribute it. And now we have two scalars multiplying times a vector in both cases. And we can just rearrange scalar multiplication. Right, just rearrange RC, rearrange dr, because those are just two scalars, just to be clear. So we're allowed to rearrange them. And now this inner piece, RU and RV, that's exactly what dV and du would be. In other words, what we have here is CT of u dt of v. So we just showed actually property 2 is satisfied. In other words, this linear transformation from the last page is a linear transformation. I know that didn't make sense. What I meant to say is the transformation we were looking at on the last page, which I had originally claimed was a linear transformation, we've just proved that it's a linear transformation by showing it satisfied the two properties here.